In the cosmic silence where distances are measured in light years and time unfolds across eons, our star breathes. For 4.5 billion years, it has been the steadfast heart of our solar system, a giver of light, a source of life. Its familiar face, a perfect circle of comforting yellow, is a constant in our skies, a celestial anchor for humanity. But the sun is no serene deity. It is a churning, incandescent sphere of unimaginable violence, a thermonuclear furnace governed by forces we are only just beginning to comprehend. Deep within its core, a relentless process of fusion crushes hydrogen into helium, unleashing the energy of 1 million nuclear bombs every single second. This energy, born in fury, begins a journey that can take 100,000 years to escape the star's crushing gravity. It percolates through the radiative zone, a dense region where photons are absorbed and re-emitted in a chaotic, staggering dance. Then it reaches the convective zone, a boiling, seething cauldron of plasma, where colossal bubbles of hot gas rise, cool, and sink like a pot of water on a stove the size of a galaxy. This constant motion, this stellar turmoil, tangles the sun's immense magnetic field into a web of invisible planet-sized knots. These lines of force, ordinarily a shield, become twisted springs of cataclysmic potential, storing energy beyond human imagination. On a Tuesday in the spring of 2025, one of these springs coiled tighter and tighter for weeks over a sunspot region, designated AR3975, finally reached its breaking point. Without warning, without a sound that could ever cross the void, the magnetic architecture of a region larger than 10 Earths reconfigured itself in a fraction of a second. A celestial synapse fired. The energy of 1 billion hydrogen bombs detonated at once. This was not fire, not combustion as we know it. It was a pure, violent release of magnetic tension, a convulsion that sent a wave of high-energy X-rays and radiation blasting outwards at the speed of light. On the scale of cosmic tempests, it registered as an X5.1, one of the most powerful solar flares of the decade, and it was aimed directly at the third planet from the Sun. For 8.5 minutes, the Earth continued its placid rotation, its 7 billion inhabitants oblivious to the silent, invisible barrage that was already crossing 93 million miles of space. Humanity has always worshipped the sun, and for good reason. Ancient Egyptians saw it as the god Ra, sailing his barge across the heavens, bringing light and order to the world each day. The Aztecs offered human sacrifices to Huitzilopochtli, their sun god, believing his cosmic battle required nourishment. To the Greeks, Helios drove a golden chariot from east to west, his presence the very definition of existence. This celestial body was perfection, a flawless orb, a divine entity. That conception was shattered in the early 17th century. Galileo Galilei, a contentious astronomer from Pisa, pointed his newly crafted telescope at the solar disk. He saw not a perfect sphere, but a blemished, freckled face. He documented these sunspots, dark, transient patches that marred the supposed perfection of the heavens. His observations suggested the sun was not immutable, that it rotated, that it was a dynamic and changing world in its own right. This was heresy, an affront to the established doctrine of a perfect, unchanging cosmos with humanity at its center. His discoveries cost him his freedom, but they ignited a revolution in thought that would forever alter our relationship with our star. Centuries later, new tools allowed us to probe its secrets further. The science of spectroscopy, pioneered by Joseph von Fraunhofer, allowed us to dissect sunlight itself, revealing dark lines in its spectrum that acted as chemical fingerprints. We learned that this distant god was made of the same elements found on Earth: hydrogen, helium, carbon, iron. The divine was rendered physical, the mysterious became material, yet a profound enigma remained the source of its power. 19th century physicists like Lord Kelvin proposed that gravity was the engine, that the sun was slowly contracting, converting gravitational potential energy into heat and light. His calculations, however, gave the sun an age of only a few tens of millions of years, a figure that flew in the face of geological evidence, suggesting an Earth that was vastly older. The puzzle would not be solved until the dawn of a new physics. Albert Einstein's iconic equation E = mc², unveiled a reality more staggering than any ancient myth. It revealed that mass itself was a form of frozen concentrated energy. If a mechanism could be found to unlock even a tiny fraction of that energy, it could power a star for billions of years. The key was the atom. Inside the sun's core, the conditions are beyond extreme. The temperature reaches 15 million degrees Celsius, and the pressure is 250 billion times that of Earth's atmosphere at sea level. In this cosmic forge, the state of matter we know is impossible. Atoms are stripped of their electrons, creating a superheated soup of protons and free electrons known as plasma. Gravity, the relentless hammer of the cosmos, smashes these protons together with such incredible force that they overcome their natural electromagnetic repulsion. Imagine trying to push the north poles of two immensely powerful magnets together. It takes a colossal amount of force. The sun's core is that force scaled to a stellar level. When these protons fuse, a miraculous transformation occurs. 4 hydrogen nuclei are forged into a single helium nucleus, but the resulting helium nucleus is slightly less massive than the 4 original protons combined. The missing mass, a tiny fraction, has not vanished. It has been converted into a pure explosive burst of energy as dictated by Einstein's law. This is nuclear fusion, the engine of the stars, the source of nearly all light and life in the universe, the X5.1 flare was a symptom of this ferocious engine, a momentary breakdown in the impossibly complex magnetic systems that contain and channel this stellar power. The first messengers of the event arrived without fanfare. At the Space Weather Prediction Center in Boulder, Colorado, an alarm blared, a sterile electronic sound belying the primordial violence it signified. Data from the GOES satellite, a sentinel in geostationary orbit, showed a spike in X-ray flux that was almost vertical. The graph shot past the M-class level, past X1, X2, X3, X4, and finally crested at X5.1. A profound quiet settled over the control room. The scientists, fluent in the language of solar physics, understood the implications immediately. On the sunlit side of the planet, from East Asia to the Pacific, the effects were instantaneous. The blast of X-rays and extreme ultraviolet radiation slammed into the highest layers of Earth's atmosphere, the ionosphere. This region, a sea of charged particles that acts as a celestial mirror for radio waves, became supercharged, energized. It began absorbing high-frequency radio signals instead of reflecting them. Pilots flying over the Pacific Ocean suddenly found their long-range communications turned to static. Ships at sea were cut off from shore. Emergency broadcasts and ham radio operators fell silent. For a period of about an hour, a vast portion of the globe was plunged into a communications blackout. This was merely the opening act. The flare itself was the muzzle flash. The cannonball was yet to come. Telescopes both on the ground and in space quickly confirmed the scientists' worst fears. The magnetic detonation had also launched a colossal cloud of solar plasma, a billion-ton bubble of protons and electrons laced with its own tangled magnetic field. A coronal mass ejection, or CME. And it was a halo event, meaning it appeared to expand in a circle from the sun, a clear sign that the eruption was heading directly for Earth. A hurricane of charged particles, a solar tsunami, was now crossing the interplanetary void at over 2 million miles per hour. Its estimated time of arrival, approximately 30 hours. The world was put on notice. This was not the first time humanity had faced the sun's fury. In September of 1859, an English amateur astronomer named Richard Carrington was in his private observatory, sketching a group of unusually large sunspots. Suddenly, he witnessed 2 patches of intensely bright and white light erupt from the sunspot group. He was so startled he thought the filter on his telescope had broken. Just 5 minutes later, the light was gone. He had become the first person to observe and record a white light solar flare. 17 hours later, the CME from that flare struck the Earth. The planet's magnetic field was thrown into a violent convulsion. The results were spectacular and terrifying. Telegraph systems, the high-tech global network of the Victorian era, went haywire. Sparks flew from telegraph machines, setting papers on fire. Operators received electric shocks. Some disconnected their batteries and found that the auroral currents alone were strong enough to power their transmissions, sending messages via the phantom electricity from the sky. The most breathtaking effect was the aurora. The northern lights, normally confined to the Arctic Circle, were seen as far south as Cuba, Mexico, and Hawaii. People in the Rocky Mountains woke up in the middle of the night thinking it was dawn. Prospectors for gold started making breakfast under the eerie, pulsating red and green glow of the sky. The Carrington Event, as it came to be known, was the largest solar storm on record. In 1859, it was a curious and disruptive spectacle. If a storm of that magnitude were to strike our technologically dependent civilization today, the consequences would be catastrophic. Our modern world is built on a fragile architecture of satellites and interconnected power grids. We have wrapped our planet in a delicate electronic nervous system, a system that is exquisitely vulnerable to the whims of our star. The 30-hour journey of the 2025 CME was a period of tense preparation across the globe. Satellite operators worked feverishly. Many non-essential satellites were placed into a safe mode. Their sensitive electronics powered down their orientation, adjusted to present the smallest possible profile to the oncoming storm. Astronauts on the International Space Station retreated to the most heavily shielded sections of the orbiting laboratory, waiting out the passage of the solar radiation storm. Power grid managers consulted their models, rerouting electricity and bringing extra generators online, preparing for the strain that was to come. It was a planetary scale bracing for impact. Then it arrived. Not with a sound, not with a tremor, but with a silent, invisible collision in the vacuum of space. The first line of defense was Earth's magnetosphere, the magnetic bubble generated by the molten iron core of our planet. This field is our unsung hero, a shield that extends for tens of thousands of miles into space, deflecting the vast majority of the solar wind and cosmic rays that would otherwise strip our atmosphere away and sterilize the surface. The CME struck this shield like a tidal wave hitting a seawall. On the sun-facing side, the magnetosphere was compressed, violently pushed down to altitudes where geostationary satellites orbit. On the night side, the field was stretched out into an immensely long magnetic tail like a windsock in a hurricane. For the hundreds of satellites in orbit, the environment became a war zone. First, a blizzard of high-energy protons accelerated by the shockwave of the CME arrived. These particles are like microscopic bullets, capable of penetrating the skin of a spacecraft and wreaking havoc on its electronics. They can flip bits in a computer's memory, changing a 1 to a 0, leading to phantom commands or corrupted software. In more severe cases, they can cause permanent damage, frying microchips, and rendering a billion-dollar piece of hardware into a useless piece of space junk. Simultaneously, the deluge of lower-energy electrons created massive static buildups on satellite surfaces. When these electrical potentials discharged, they created miniature lightning strikes capable of short-circuiting critical systems. In low Earth orbit, home to thousands of satellites like the Starlink constellation and the Hubble Space Telescope, a different threat emerged. The energy dumped into the upper atmosphere caused it to heat up and expand like a balloon. The air, though incredibly thin at these altitudes, became denser. This increased atmospheric drag on satellites, slowing them down and causing their orbits to decay more rapidly. The careful, predictable clockwork of orbital mechanics was thrown into disarray, increasing the risk of collisions that could trigger a cascade of debris, a nightmare scenario known as the Kessler syndrome. GPS signals, which must travel through this turbulent, charged ionosphere, became unreliable. Navigation systems for aircraft and ships were compromised. Financial transactions which rely on precise GPS timing were disrupted. The intricate web of global commerce and logistics began to fray. As the chaos unfolded in orbit, a far more dangerous threat was brewing on the ground. The violent shaking of Earth's magnetic field induced powerful electrical currents in the planet's crust. These geomagnetically induced currents, or GICs, sought the path of least resistance. And we have conveniently provided them with our sprawling, continent-spanning networks of power lines. Imagine the Earth itself becoming a giant electrical generator. The moving magnetic field is the prime mover, and the thousands of miles of conductive power lines are the coils. These GICs are not the alternating current AC our grids are designed for, but a quasi-direct current DC. When this alien DC electricity flows into the massive transformers at electrical substations, it can cause them to saturate. The iron cores of the transformers, designed for the smooth cyclical flow of AC, are pushed into a state where they can no longer absorb more magnetic flux. They begin to overheat rapidly. The harmonic vibrations change from a steady hum to a pained guttural groan. Protective relays sensing the abnormal currents can trip, taking the transformer offline to prevent its destruction. If this happens to one key substation, the grid can usually compensate, but during a major geomagnetic storm, this happens to dozens or even hundreds of substations simultaneously. The result is a cascading failure. As one station goes offline, its load is shunted to others which are already under strain. They too are overwhelmed and they trip. The blackout spreads like a contagion across the network. This is what happened in Quebec in 1989, when a much weaker storm plunged 6 million people into darkness for 9 hours. The X5.1 storm was far more potent. Across North America, Europe and Asia, grid operators watched in horror as their systems buckled. In some locations, the safety systems failed or were too slow. Transformers behemoths the size of a small house, weighing hundreds of tons, overheated to the point of catastrophic failure. Their insulating oil vaporized, causing massive explosions and fires that sent plumes of black smoke into the sky. These are not devices that can be easily replaced. Each one is custom built, takes months or even years to manufacture, and costs millions of dollars. The lights began to go out, but as darkness fell on the ground, the sky was being set ablaze. The same particles that were wreaking havoc on our technology were also creating the most spectacular celestial light show in modern history. The energized protons and electrons from the CME, captured by Earth's magnetic field, were funneled down the magnetic field lines towards the polar regions. As they cascaded into the upper atmosphere, they smashed into atoms of oxygen and nitrogen at thousands of miles per second. This cosmic collision excited the atmospheric atoms, kicking their electrons into higher energy states. As the electrons fell back to their normal state, they released their excess energy as photons of light. The color of the light depended on the atom struck and the altitude of the collision. Oxygen at high altitudes produced a rare, haunting blood-red glow. Oxygen at lower altitudes created the most common color, a vibrant, otherworldly green. Nitrogen atoms contributed hues of blue and deep purple. The storm was so intense that the auroral oval, the ring of light normally centered on the magnetic poles, expanded dramatically. It wasn't just a northern light or a southern light, it became a global light. For the first time in recorded history, the Aurora Borealis reached Mexico. In Mexico City, a metropolis of 20 million people, the sky began to shimmer. Residents, accustomed to the hazy glow of city lights, stepped out onto their balconies and rooftops, their phones held aloft. They witnessed a sky they had only seen in documentaries and photographs. Vast, silent curtains of emerald green and ruby red light danced and pulsed overhead, stretching from one horizon to the other. The spectacle was not confined to one continent. In the Sahara Desert, nomadic tribesmen watched as the dunes were bathed in an ethereal luminescence that shifted and flowed like the sand itself. In northern India, the sky above the Himalayas took on a crimson hue, as if the mountains were reflecting a fire from the heavens. The awe was universal, a shared human experience that transcended culture and language. It was a moment of profound connection to the cosmos, a visceral reminder that our world is part of a much larger, more dynamic universe. This was the terrifying paradox of the storm. On the ground, our civilization was being crippled by the very same forces that were painting a masterpiece across the night sky. The beauty was a direct consequence of the danger. The vibrant colors were the visual evidence of our planet's atmosphere being bombarded by a solar tempest. It was a return to a primal state of being. For millennia, our ancestors looked up at these celestial displays with a mixture of fear and wonder. They saw them as bridges to the afterlife, as battles between gods, as omens of war or famine. They created myths and legends to explain the inexplicable. Now we understand the physics. We know about magnetohydrodynamics, particle acceleration, and atomic emission spectra. But does this knowledge diminish the wonder, or does it in fact enhance it? To know that we are witnessing the interaction of our planet's own magnetic heart with the fiery breath of its parent star is arguably more profound than any ancient myth. It connects us directly to the fundamental forces that govern the cosmos. In the days that followed the storm, the full extent of the damage became clear. Dozens of satellites were declared total losses, their electronics fried beyond repair. Hundreds more had their operational lifespans significantly shortened by the intense radiation. The orbital environment was more cluttered, the risk of collision permanently elevated. The power grid was a patchwork of blackouts and brownouts. While engineers worked heroically restoring power to most urban centers within a week, some regions with destroyed transformers faced months without reliable electricity. The economic cost was staggering, measured in the hundreds of billions of dollars from lost productivity, damaged infrastructure, and disrupted supply chains. The X5.1 event of 2025 was a global wake-up call. It was a shot across the bow, a warning from the sun. It was powerful enough to cause significant disruption, but it was not a civilization-ending catastrophe. It was not another Carrington event. The chilling realization was that it could have been much, much worse. A flare 10 times stronger, an X50, is not a matter of science fiction. The geological record preserved in ice cores and tree rings tells us that such superstorms have happened in the past and will happen again. We were lucky. The next time we might not be. The event spurred a renewed sense of urgency in our efforts to understand and predict space weather. Missions like the Parker Solar Probe, a spacecraft literally flying through the sun's outer corona, touching the face of the star, provided invaluable data. The Solar Orbiter, a joint mission between NASA and the European Space Agency, captured the highest resolution images of the sun in history, revealing the intricate magnetic dance that leads to these explosive events. On Earth, artificial intelligence began to sift through decades of solar data, learning to recognize the subtle precursors to major flares, improving our forecast lead times from hours to days. Nations began the long, expensive process of hardening their electrical grids, installing devices to block the flow of GICs, and building up a strategic reserve of spare transformers. We began to treat the threat of solar weather with the same gravity as we treat hurricanes, earthquakes, and other terrestrial disasters. We live in a cosmic shooting gallery on a small, fragile world with a thin veil of atmosphere and an invisible magnetic shield. We are utterly dependent on a star that is by its very nature violent and unpredictable. It is the source of our warmth, the engine of our climate, the foundation of our food chain. The light that streams through our windows travelled for 8.5 minutes from a nuclear inferno. Every atom in our bodies, heavier than hydrogen and helium, was forged in the heart of a star like our sun long ago. We are in the most literal sense children of the stars. The 2025 solar storm was a harsh but necessary reminder of this profound and humbling truth. It exposed our modern vulnerability, but it also reignited our ancient sense of awe. It forced us to look up past our screens and our immediate concerns and to contemplate the immense, beautiful, and terrifying power that governs our existence. Our challenge is to continue to learn, to innovate, and to build a civilization resilient enough to withstand the fury of the very star that gave us life. Because the sun will continue to churn, its magnetic fields will continue to twist, and sooner or later another storm will come, and we must be ready.